Hi there, everyone. I want to give you a quick overview on Chapter 2. So I'm looking here in our shared OneNote notebook for Chem 130, and I'm going to expand this. I'm in the Chapter 2 tab, and I'm looking at the lecture PowerPoints. We started talking about this in class the other day in our live session, but I'm going to just go back over this. So in terms of measurement in science, measurement is kind of what makes science science. Without measurement, I don't think science could exist. When you measure things, you have to have units, right? Like meters here is a unit. So you know what you're talking about. And we're looking here at two things that are extreme scales. You've got the distance from the Earth to the Sun, and then you've got this very small microscopic worm that exists in hydrothermal vents under the ocean. So we'll learn a little bit about using these measuring units and converting back and forth between them and dealing with very large and very small numbers. So the way that we express really large or really small numbers in science is through something called scientific notation. In scientific notation, you've got some number that is, I'm going to just write as x dot x, and that number, which might be different numerals there, is going to be between 1 and 10. It won't ever be 10. It could be less than 10, and it won't ever be below 1. And then we multiply it by 10 raised to some power, and that exponent up there is kind of moves the decimal point back and forth as we convert back and forth between those. If that exponent is negative, if a is negative, then that means that the number is smaller than 1. When you write it out in a decimal form, if a is positive, that means that typically the number is greater than 1. And that tells you which way the decimal moves. Of course, if I had 10 to the 0, that is by definition 1. So the number 1 in scientific notation would technically be written as 1 times 10 to the 0. That'd be equal to 1. If I say 1 times 10 to the 0, 10 to the negative 1, that's going to be 0.1. If I say 1 times 10 to the first, that's going to be 10. Like so. So the way we read this, if I have over here, this number is 2.14 times 10 to the negative third. So that negative 3 tells me if I want to put this in decimal form, I'm going to move the decimal point over 3 places, going back to the left. So the decimal form, that number is 0.00214. And if we look at Avogadro's number here, which is given the symbol N sub A, 6.02 times 10 to the 23rd, which is the number of atoms that are in a mole, that is a really large number. When we write it out in decimal form, we've moved that decimal point 23 places that way, in essence. So if you count there, hopefully I counted the right number of places to get that in decimal form. In the old days, when scientists used slide rules, you could only do the 1 to 10 part on the slide rule, and the part that was on a power of 10 was carried along either on paper or in your head. The power of 10 thing is kind of useful because there are some simple rules. If you're multiplying two things that are expressed as powers of 10s, you just add those exponents together to get it. So 10 to the second times 10 to the third is 10 to the fifth. So if I have 100 students pay me $1,000, that's $100,000, which is what 10 to the fifth is. If you divide, you subtract the exponents. So if I have $1,000 and I split it up between 100 students, each student only gets $10, as you see in that example. When you're typing stuff into your calculator, you want to be careful. Usually in a calculator, you'll see this E or EE notation that's written right here as the way of indicating that you're in scientific notation. If you're using something in a scientific notation type thing, what I'm pointing out here is E EE, or E means in calculator speak, times 10 to blank, whatever that new exponent is. So in the TI-84, the really fancy TI-84 calculators, they made EE a second function, something for which I will probably never forgive Texas Instruments. But so what you have to do to get it is hit the second button and then the comma button, because the comma button has a EE on top of it. So typing in Avogadro's number, the number I had over up on the right, I would type in 6.02 second, comma 23, and that's 6.02 times 10 to the 23rd, which will show up in your calculator as something like this, 6.02 E or EE23, depending on the calculator. If you instead use the caret, that's this term here, and you type the number in as 6.02 times 10 caret 23, that'll usually work, but there are times when you will come into trouble doing that, and so I'd encourage you not to do that one. We can use this sort of thing as an example here, and so I said this question basically, so here's a question. If I have 3.01 times 10 to the 23rd atoms, how many moles is that? So to tackle this problem, I set up what I'm looking for as x moles, and then I set that equal to the information I'm given, the 3.01 times 10 to the 23rd atoms, and then I create this conversion factor here. That's based on the Avogadro's number, that basically 1 mole divided by 6.02 times 10 to the 23rd atoms, that is conceptually equal to 1. 1 mole is the same thing as 6.02 times 10 to the 23rd atoms. So we can cancel out atoms there and then do the division, which is what the line in the middle means, and that's going to get us the moles. This 3 is just the number of the slide. It's not involved in the calculation there. Now, if I do that in my calculator, if I do it the first way, where I use the second comma method, right? So that's 2 keystrokes there. And I do that, I get the correct answer, which is half a mole. That's good. If I do it the other way, where I use the caret 23rd thing, times 10 to the caret 23rd divided by 6.02 times 10 to the caret 23rd, I get a very wrong answer, which is 5 times 10 to the 10 to the 45th. That's called a hierarchy error, and that's why I encourage you to use the second comma instead of the times 10 to the caret thing. Here's a slide illustrating the powers of 10 and showing how those are, if we write 10 to the third, that means we're multiplying 10 by itself 3 times, and that's 1,000. If we write 10 to the negative third, that's 1 over 10 multiplied by itself 3 times, and that's 0.001. Here are some other examples showing different values, how this 5.1 times 10 to whatever it is changes as we change the exponent on 10 there. And going back and forth between standard and scientific notation, you're going to count how many places you need to move the decimal and then put in the appropriate power of 10. So with 2,500,000 liters, which is a lot, but that might be a pretty small swimming pool actually. That is, we move over to our left 6 times, so we're moving the decimal from here over to here. Since we're going to the left, the number is bigger than 1, so we're going to have a positive number. We moved it 6 times, and when we get to the point where we have a number between 1 and 10, remember that's our point where we're okay with it, we've got that number. So you can do that by hand, and if you're moving it to the left, like in this case right here, we moved it, I'm sorry, to the right, we're moving it to the right 7 times until we get something that's between 1 and 10, so that's 10 to the negative 7, going that way. And here's some examples of going from standard to scientific, or scientific to standard again. And so we're taking that value, moving the decimal point in the proper direction, and we get our values. And again, if we have a negative exponent, our value is less than 1. If we have a positive exponent, our value is more than 1. Here again is that example calculation that I did over on the right. What this is basically saying is that we can do this like the scientists with the slide rules. We can separate the coefficient parts and the exponent parts into two different calculations. So the example I have here is that the one I gave you before. We were counting the number, or determining the number of moles in 3.01 times 10 to the 23rd atoms. And to do that, we were multiplying by the conversion factor 1 mole over 6.02 times 10 to the 23rd atoms. And if I do the coefficient part, that's 3.01 divided by 6.02, that's 0.5. And if I do the exponent part, 10 to the 23rd divided by 10 to the 23rd is 10 to the 0. 10 to the 0, of course, is 1. So 0.5 divided by 1 is 0.5 moles. So we could actually have probably done that one in our head. A lot of times you can come up with kind of ballpark estimates or numbers, and that'll help. So here's an example where they're subtracting the exponents. So 8.4 divided by 2, that's going to be a little more than 4, right? 10 to the 7th divided by 10 to the 3rd is going to be 10 to the 7 minus 3. So it's going to be somewhere around 4 times 10 to the 4th. Yeah, so that would be my estimate. The actual answer is that. So that's a pretty good estimate. We're not off by too much. A lot of times when you're doing a calculation with a calculator, if you make a mistake, you get the numbers out of order or get the decimal point in the wrong place or something, don't catch it unless you make that estimate up front. That's really how you catch those mistakes. And I really think catching mistakes might be more important than not making mistakes. So now, if you have a situation where you're typing a number into a calculator to do this, there are times you can violate it. So I guess initially here we're talking about what happens when these two numbers come out to be something greater than 10. So this one came out to be 15 here. The power of 10 part came to 10 to the 12th. What we have to do is, if we move this back that way 1 decimal, that means we've got to increase this power once. So essentially we're dividing this side by 10, multiplying this side by 10 to get 1.5 times 10 to the 13th. And that's outlined over here on the side. One trick that's useful to do, you can, if you're typing into a calculator a number, it's okay to violate that rule. And so we talk about light is important in terms of giving us insight into the structure of an atom. So we talk about 700 nanometers of light is the wavelength. The symbol for that is this Greek letter lambda. That is the wavelength of light that is the edge of the visible spectrum for us. So it's the bluest light that our eyes will detect is around 700 nanometers. And the way I would type that into a calculator in a problem where I needed to have the units in meters is I would just go ahead and type 700 second, comma, and again that's my EE thing on my calculator, negative, which on the TI is a little bracket negative sign on it. Some things will be plus minus, and then put the number 9 in. That would be how I would enter that. And what I've done there is I put 10 to the negative 9 in because that means the same thing as that prefix nano, and you'll learn a bunch of these prefixes before. If you go and look at in the TI-84 under mode, you can set the calculator in either normal, scientific, and engineering mode. And so I have 3 examples of a number. So the normal mode for this is a bunch of zeros and 7. The scientific notation, that's 7 times 10 to the negative 7th. What's called engineering notation it's like scientific notation, except the exponent there is always something that's divisible by 3. So actually that would have been the correct expression for this value in engineering notation. It'd be 700 times 10 to the negative 9th. And here's some commentary on calculators. This is a TI 36, which is a fine calculator, very inexpensive calculator. I think I mentioned this in class the other day, but I'll say this again because I always say it. The calculator is a very important tool to you in your chemistry class, and in your physics class, and your math class. And in fact, I say it's an analogy that the calculator to you is like a rifle for a person in the Army that's going through boot training. And if you've seen movies of people going through boot training, they learn how to take their rifle apart and put it back together blindfolded and things like that. They really know how to use it. That's absolutely the approach you should take. You should get a calculator that you're going to use. If your math class, for example, requires you to use those TI 80 somethings, then go ahead and go whole hog into the TI 80 somethings and learn everything you can about that calculator. Of course, the great world that we live in now, it's all just a YouTube video away. So, you can, if you're trying to do, equilibrium problems in a chemistry class with a TI 84 calculator, you can type that into YouTube and get, a dozen videos of people telling you tricks that they know about doing that. So the power to learn is really in your hands. So again, back to this idea of units. So to measure things, you have to have kind of an agreed upon thing. Most of us, if we grew up in the United States, most of us grew up with English units. So we know what a gallon is, we know what a mile is, we know what a yard and a foot is, those kind of things. The SI system, which is based on nature, is a system that's more logical and is used in science and is used generally worldwide more. The United States is one of the few holdouts using the English system. This points out that you do have units sometimes where you have mathematical relationships in units here. So they talk about, I always remember that when I got my driver's license, the maximum speed limit was 55 mph, which means miles per hour. So that's 55 miles divided by hours, and that comes out to be 88 kilometers per hour. So 88 kilometers per hour, just a couple that I remember. So this is a case where we've got units that are related by a mathematical relationship, and we're going to manipulate these units mathematically. If I want to go, let's say I want to go 110 kilometers away, and I can go 88 kilometers per hour. Well, I want to figure out how long I'm going to do that. I could put 88 kilometers down here. Well, how many hours does it take me to go 88 kilometers? According to this, that's 88 kilometers in 1 hour. Kilometers can cancel out, and so it'll take me 110 divided by 88 hours, and we could mathematically figure out that's a little more than an hour and a quarter, maybe even a little less than that. We can plug it in the calculator. Using the units will help you figure out how to do the problems. Here are some common English and metric units. You've got some conversion factors over here in the last column between the metric and English units. Usually the expectations in science is that you're going to know the metric conversions, the going from metric to metric. So centimeters to meters, for example, is something you'd be expected to know, and there's a system to it. It's not hard to know. The relationship going from one to the other typically will give you some sort of a conversion factor that you can pick up and use. It may not be the one you want. You may have to deal with it. Like for example, I don't think I've ever given anyone that 1 meter is 3.280 feet. What I usually do is tell people that 1 inch is 2.54 centimeters. And that's kind of a handy one to remember, that 4 inches is about 10 centimeters. So if you want to do a rough comparison. The assumption that I'm making in that, and I don't want to make this assumption, so if I ever should make it, let me know that you need this. If you don't know the English unit conversions, then those are those will be given if you need them. We just kind of assume everybody knows that 12 inches is a foot and 3 foot is a yard and 5,280 feet is a mile and things like that. Anytime we have a conversion factor like that, of course, that kind of thing gives us, that equality gives us 2 conversion factors. So I could say 2.54 centimeters over 1 inch, or 1 inch over 2.54 centimeters. If I wanted to ballpark how tall I am in centimeters, I might be something like 70 inches tall. And just using this one as a ballpark, 10 centimeters for every 4 inches. Inches cancel out. 70 divided by 4 is, well, it'd be, if it was 80, it would be 20. So it's not going to be that. It's going to be 1, 2.5, 4 lesses than 20. So I'm gonna think it's gonna be 17.5. That's the 70 divided by 4 times 10 centimeters. So about 175 centimeters. Don't hold that to me. I'm probably shorter than I used to be. So the metric system, or the SI system, we've got these fundamental units, and we tend to work with the ones that are in red here: the mass, length, time, temperature. We'll also use this amount a lot, the moles. That's one that we'll do. And then when you mathematically manipulate a unit, that's called a derived unit. And so there are a lot of derived units. For example, the unit of force is called the Newton. Won't use it in chemistry much, but you'll use it in physics. And a Newton is a kilogram meter per second squared. So it's got several different units that are used to do that. Oftentimes in chemistry, we'll, instead of using kilograms per cubic meter, we'll use grams per cubic centimeter. But that's another way of expressing density. Every time you see that, it kind of gives you a suggestion of what the equation is. Volume would be 3 lengths. So if I have a cube, the length times width times side would be the volume. Velocity is going to be distance divided by time. Density is going to be mass divided by volume, which is what meters cubes measures. So you can sort of see the equation expressed in the units there. The metric system has a power of 10 is used with these prefixes, and so you see here these prefixes, which are based on Greek words, and those prefixes have symbols, and then those go with powers of 10. So for example, 1 megawatt, okay, watts a unit of power, that's going to be 1 million, 1 times 10 to the 6th watts. And so that'd be 1 followed by 6 zeros. And that'd be a capital W, I think, for that unit. 2 millimeters, okay, is going to be 2 milli here is 1/1000th, or 10 to the negative 3 meters. And that would actually, that's fine in scientific notation. If I want to go to regular notation, that's going to be 0.002 meters. So we can use those to convert back and forth and scale our units to ones that make sense. Couple of examples here. So they use megaamps, I use megawatts, so you can see some examples in here that I'm not going to go through for you, but you can read those and see. You can absolutely pause the video and check those out. When we're talking about measurements, we also talk about how good are the measurements. The balance here that we have, this is an electronic balance. It's probably a quite expensive electronic balance. And how many decimal places we can claim, how many places past the decimal we can claim to know is one of the ways we deal with the quality of measurements. We talk about accuracy, first of all. Is it an accurate measurement? And a nice, expensive, probably $10,000 or more scientific balance here is going to be accurate all the way out to the tenth of a milligram, right? So this is, if we say 0.1, that would be a decigram. 0.01 would be a centigram. 0.001 would be a milligram. And so going out three zeros and one, that is a tenth of a milligram. That is a very, very precise measurement. And you see that we got all these screens around the balance there because air currents can affect that. If you take your dog to the vet and you get the dog weighed, that might be accurate to about a tenth of a kilogram, right? Which is that's 100 grams. So what it's saying is that the dog's weight might be off by plus or minus 100 grams. That's setting aside issues of getting your dog to sit on the scale, which is a problem with my dogs at least. So we're talking there about this concept of precision. Precision is how consistently do you get the same value? If you're measuring a weight, how consistently is the same value given? Does the balance return the same value every time? You might think that naively that they would always do that. They don't. And then accuracy is the issue of how reliable they are. Do they reflect the true value? And you have to have some kind of standard to check that out with. So if you were checking to see if your balance is working, you might use a preserved standard that someone has. The nickel is a good standard. It's a 5 gram weight pretty precisely. And, or you might use a measured volume of water, which is, if you know the volume and the temperature of the water, you can calculate its mass pretty accurately, even at very small amounts. And so those are some standards we can use. Here is the classic image of precision and accuracy. You're looking at the dartboard here. And if you consider the average position relative to the center of the darts here, on this one up here, they're hitting the target and hitting it reliably. So this is accurate and precise. The second case over here, and this one, it might be one if you were using a rifle, for example, and firing on a target. If your sights were out one particular way, but the rifle put the bullets in that same area every time, that suggests that the rifle itself is probably shooting the bullet straight, but the sights are getting you off just a little bit. So this is considered to be precise, but it's not accurate. It's not hitting it. The case down here at the bottom, accurate, not precise. If you think about these, the average position of these guys, they kind of are averaging out about at the middle of it. If you pair these two up and think about it, the average value is probably somewhere up there. So that might be, if you average all those values, that might give you a pretty accurate value, but they're not precise. And then the last case is the worst case, where it's neither precise nor accurate. So when we have a device, some sort of measuring device like a ruler or, in this case, a beaker or a graduated cylinder. This is a graduated cylinder. This is a beaker. Beakers are very non-precise, and the rule of thumb is if you look at the smallest division. Okay, so if we look here at this guy, so let's consider this line and that line. So the line there represents 90. It's the line between 80 and 100, so it's 90. That's 100, so that difference is 10 milliliters. We can multiply that by 1/10, and we can probably estimate to within about plus or minus 1 milliliter. So I'll say plus or minus 1 milliliter. So we're justified then in expressing values in the ones place because we can do plus or minus 1 milliliter. In this one, if you look at these lines between those, you have to count carefully, but that's 30, that's 29, that's 1 milliliter, and 1/10 of 1 milliliter is 0.1 milliliter. So we're justified in expressing a value out to the tenths place, so we could get more significant digits or a more precise reading from the graduated cylinder. Beaker, 45 cents. Graduated cylinder, 10 to 20 bucks, depending on that. So you can pay for that precision as well. So be careful in the lab, don't break the grad cylinders. Now, one of the difficult concepts that folks encounter in chemistry is we start thinking about not only numbers and data, but also how well we know those numbers and data, which is really a very liberal arts thing to think about. You know, to what extent do we have knowledge? So we have this concept of significant digits or significant figures. And what that refers to, if you think about all the numbers that are making up the number, which ones are significant, which ones are not significant, which means which ones do we not really know. And the rule's pretty simple. If you have a numeral that's 1 to 9, it's going to be significant. If it's a 0, it's significant if, one thing, it can be significant if it is between two non-zeros. It can be significant if there's a decimal point in the number and it's to the right of that decimal point, or that decimal point at the end, but not at the beginning necessarily, unless it's between two non-zeros, or if there's a decimal point to the that the zero is to the left of. So if I've got 101, that has 3 sig figs. The number in the middle is significant. If I have 0.000102440, this 0 is significant because it's between 2. This 0 is significant because it's a decimal at the right of the end. These zeros are all non-significant because they're called placeholders. And they would disappear if we put this in scientific notation. So to put this in scientific notation, I'm going to go over 1, 2, 3, 4. So I'm going to have 1.0240 times 10 to the negative fourth is that number. And now we see that significant 0 and this significant 0 remain. If I write 200, that's only one significant figure, unless that decimal point is there. If I write 200 with a decimal point, that's 3 significant figures. If I want to write 200 to 2 significant figures, I'd have to say 2.0 times 10 to the second. That's the version with 2 significant figures. So you have those rules here about the zeros, slightly different version of them, I'm sure. And again, the best thing you can do is try to practice some of those problems with those. So here are some exercises about identifying significant figures. And again, in this case, you've got these leading zeros that are not significant, that are placeholders for the decimal on this one. And here is a case where we have the trailing zeros. And again, it kind of depends on where the decimal point is or where a non-zero value may be there. When you have large numbers like that, it's kind of hard to express that. Sometimes we use this plus or minus indication here to say that, okay, we know that it's 10,000 out to this point, and there it could be, basically we're saying this is between 10,100 and 9,900. That's that range. That's 10,000 plus 100 and 10,000 minus 100. And then we can also express it. To express that the limit is at that point, we could put it in scientific notation and end that first number there that shows that we've got the 3 sig figs. So here's a summary of the rules about what can be significant, what may not be significant, and what may be significant. Again, practice is going to help you with those. There are some numbers that significant figures don't apply to. If you have a counted value, there is no error in that unless it's not really a count, it's an estimate. If you have a defined value, like a conversion factor, those significant figures don't apply to those as well. So when you do calculations with significant figures, so you see here that we've got a sphere or a circle that we're measuring there with our centimeter ruler, and that value comes out to be around 2.7. Again, we're using the rule. This is 1 centimeter, so we can estimate 1/10 of that, so plus or minus 1 centimeter. So when we say 2.7, we're saying it's somewhere between 2.6 and 2.8. That's 2.7 plus 0.1 and 2.7 minus 0.1. And that's one of the things that's important, is to remember that significant figures really come from measurement, even though a lot of times in problems you don't see that measurement. Now, when we go to calculate the circumference is the diameter times pi. Pi, of course, is 3.14159, whatever that number goes on. It's a number that's defined for quite a few significant figures. If we calculate that out, and what they've done here is they've calculated using the 2.7 minus 0.1 and the 2.7 plus 0.1, what you see is you get a variation that again shows up in that tenths place. The average of those values would be 8.5, but what we wind up with here is that we had two significant figures in this number. We only can claim two significant figures in this number. That's the only reasonable claim that we can make there. So those are the rules about manipulating significant figures when we do calculations. So when we multiply or divide, we report the same number of digits or in the least precise starting measurement. So you see this example here where you're dividing miles, which we have 4 sig figs by time, which we only have 2 sig figs, so we can only report 2 sig figs at the end. We have to round our answer we get in our calculator down to 2 sig figs, or in this case up to 2 sig figs. 60.6 rounds up to 61. When we do addition and subtraction, it's good to think of it in this kind of columnar method. We round it to the least precise place that's common to both of the measurements. So 0.432 miles plus 18.1 miles, this is the last common or the least common significant place. So we round there to, and that gives us, wind up with 3 sig figs. It's not a convenient kind of rule. You can't, in this case it happens to work out that both numbers have 3 sig figs and the answer has 3 sig figs. That's not always going to be the case. If it was 0.44 and 18.2, for example, that's a 3 sig fig, and a 2 sig fig number, a 2 sig fig at the top, that's going to be 18.64. We're going to have to round it to that least common place, not to 2, so that would still be 18.6 miles in this case, with those different values. And what we do if we're doing a multiple step calculation is that we're going to wait till the very end to do the rounding. We'll carry those extra decimal places in our calculator until we get to the end. So here is an example of a set of measurements, and based on those set of measurements, we can come up with an average value, and we are told that all the 3 samples have 2.31 liters. So this is the total mass, the 35.869, and the total volume we're dividing by to get the volume per liter. And then we have to round that to 3 sig figs because we've only got 3 sig figs in the bottom number. We only have 4 sig figs here because the least common place gives us 4 sig figs. So that's an addition sig fig and then a calculation sig fig. And again, we would carry this whole number over into the calculator. So we didn't round it there, but we just recognized that even though we've written 5, right, only 4 of them are really significant. That's the best way to avoid error. And if you ever find teeny tiny differences between your answers and a answer on a exam or answer in the back of the book, oftentimes it's going to be a rounding thing when you round at different points. So talking about conversions a little bit more, we're going to do something called dimensional analysis, and you see here the version of that where we've got a conversion factor of some kind here that's milligrams per milliliter, and that's going to let us, that's actually density being used as a conversion factor to calculate the milligrams in 15 milliliter sample. And this is an example of getting area. So the area is equal to the length times the width. So 10 feet by 10 feet is 100 square foot of looks like flooring in that case. So if we're trying to do this sort of conversion going from 231 milligrams to grams, the fact that 1,000 milligrams are 1 grams, which we get from the definition of the prefix milli, gives us 2 conversion factors. You know, we got the one with 1,000 milligrams on the top and the other one with 1,000 milligrams on the bottom and 1 gram on the top. And then we decide which version we want to use based on what units we have and what units we want to get to. So here we have milligrams. So we put milligrams on the bottom here because milligrams divided by milligrams, anything divided by itself is 1. So that cancels out. And that leaves us with units of grams, which is what we want our answer to be in. One of the tricks to chemistry is learning all the different ways to recognize the different conversion factors that are out there. So here's an example calculating the inches in 326 centimeters. And again, we select this version of the conversion factor to do it. If we use the wrong version, right, then we get units that don't make sense. We've got centimeters times centimeters divided by inches, so we got the wrong units, and that tells us that this would be the wrong way of doing it. So if you're careful about those units, you shouldn't go wrong. Here we are using the speed of light as a value, and we're going to convert it from meters per second to miles per hour. And so what we have to do is 2 conversions. The first step is we start out with that 3.00 times 10 to the 8th meters per second. So we write it here. And they started with the conversion of miles to meters. Well, so we know that meters are going to go on the bottom, so that's going to cancel out. So 1609.3 is 1 mile. So at this point I can say meters divided by meters is 1. It cancels out. So if I calculated this number, it would be miles per second. And then to get seconds into hours, 60 minutes per hour times 60 seconds per hour gives us 3,600 seconds in an hour. And so this would, seconds and seconds now cancel out. We have seconds written on the top to cancel the seconds on the bottom here. And that gives us this answer that's right there. That's in miles per hour. Here's the volume calculation. 1,000 cubic centimeters, by the way, is 1 liter, or 1,000 milliliters. Common units of volume. You all probably know what a 2-liter bottle looks like. And those are also sometimes called a centimeter cubed, is also known as a cc, and some folks, medical folks, tend to do that. And we pick the right unit to talk about for different things. So if we're talking about shipping containers, you might be talking cubic meters. If we're talking about giving somebody an injection, that might be in milliliters or cubic centimeters. And if we're talking about a drink, that unit might be decimeters cubed. Actually, a decimeter cubed is actually the same thing as a liter, so that'd be a pretty big drink. So maybe a quarter of a decimeter cubed might be what you're having. So the liter here, they give us a common unit of volume. They say that's about the same as the volume of a tissue box or a large soft drink. I don't think that's I mean, that looks like a giant drink from Wendy's maybe. That's not the red Solo cup. The red Solo cup is smaller. A can of drink, for example, that you get, that's going to be, those are 355 milliliters, which is a 12-ounce can. And I have my 12-ounce can of Diet Mountain Dew here with me to keep my voice from totally going flat while we're doing this. Okay. So we talked about a cubic decimeter being the same as a liter. So we can calculate here that a cubic decimeter, if you think about our cube here, our imaginary cube that we're talking about, if each side of this cube is 1 meter, well, that's 10 decimeters because 1 decimeter is a tenth of a cube. So our volume will be 10 decimeters times 10 decimeters times 10 decimeters in that unit. So that's 1,000 decimeters cubed. The volume would also be 1 meter times 1 meter times 1 meter, which is a meter cubed. So a meter cubed is the same thing as 1,000 decimeters cubed. Other examples here, calculating cubic centimeters in a meter, and example problems with fluid conversions and times here, and determining how much gets delivered in IV fluid, which of course is a very important thing in medical things. Density is that relationship between mass and volume, and that's the formula again. And density is important in terms of whether things sink or float. So the kayaker is floating because the total density of the kayak and the kayaker is less than the density of water, which is 1. Here's a sample calculation of density for mass and volume with correct sig fiction. Here's another example, and here's an example. You're using density here as essentially a conversion factor to figure out how much mass you have in a cube of a certain size, it's a cube of a certain size there, centimeters cubed. And with that, we're going to wrap up here. There's just some of the common densities are listed there, so we're getting toward pretty close to the end. More examples that we'll see as we do some problems. Oh yeah, we do have to talk briefly about temperature, and I want to get that in. We talk about 3 scales really. There's the temperature in terms of Fahrenheit that we all know. There's a scale called the Kelvin scale and the Celsius scale, and we probably use the Celsius scale more for chemistry, although sometimes we will use the Kelvin scale. Absolute 0 is 0 in the Kelvin scale. 273 is the freezing point of water in the Kelvin scale. 373 is the boiling point of water in the Kelvin scale. And you may have noticed that 100 degree Kelvin here is the same as 100 degrees C here. That Celsius and Kelvin are in the same size degree. We don't say degrees Kelvin, by the way, we just call them kelvins. This points out that in that range between the freezing and boiling point of water, 180 degrees Fahrenheit occur while you have 100 degrees Celsius. That means the degrees Celsius is bigger, and you'll see that show up in the conversion factor. So here is the conversion factor if we're going from Celsius to Fahrenheit, this is 180 over 100. If you work that fraction down, it's 9 to 5. This is to correct for the 0 point. The 0 point in Celsius is 0. The freezing point, or rather, of water in Celsius is 0, and the freezing point of water is 32. So we have to add 32